Good evening, everyone. Am I audible? Okay, so I think let's start today's session. I hope I am audible for everyone. In between, if you face any problem, please let me know. Okay, before starting the session, let me introduce myself. I am Harsha from IIT Tirupati, a research scholar. So we will be taking the week 2 session of the Introduction to Abstract Algebra. And in the last week, actually, sir has covered about more about the equivalence relation and all. And other than that, he started group. Okay, in between that functions on to function one function, those things are already defined, and also the group monoid, those kind of concept also started. So more about group and all you might have seen on week 3 also. Week 3 is also the continuation. So the problems will be depending on the week 2. So we will be doing the related problem. So it will help you in solving the assignment. Okay. So first we will start with the first question. So the question is, which of the following statements are correct? Okay. So we have 3 statements here. You can tell what are all the correct statements from these 3. So first question is, if A is both countable and infinite, then there is a bijection between A and n, where n denotes the set of all natural numbers. So can you tell whether first one is correct or not? Yeah, it is true. Actually, we will see what what countable means or what infinite means. Then we will see why it is the correct one. So given that A is countable and infinite. Countable means we have already seen in the class. Countable means either finite or denumerable. Correct? So what is finite means? Finite means we can just tell there are some 5 number of elements or n number of elements like that. So finite means we can say cardinality of A equal to n for some positive integer n. What is denumerable means? Denumerable means there exists a bijection from A to n. That means we can associate the elements of A with the n. That means corresponding to each element, we can list it as A1, A2, A3, etc. like that. Okay. So what countable means? In this sense, we can write A equal to A1, A2, etc. It is going infinitely. It denumerable means it is not like some. It doesn't stop at some finite stage. Okay. When it stops at some nth stage an, then it will become finite. Okay. In this case, denumerable means it is bijection with n. What will be the bijection? A1 is mapping to 1, A2 is mapping to 2, and so on. So this is our set n, right? So like this we can associate A and n with the bijection. Okay. So this is denumerable. So what is the question? It is given that it is countable and infinite. So we have given countable, then it can be either finite or denumerable. But what we have, it is infinite. That means it is not finite. So we have only other cases denumerable, countable and denumerable then. Okay, countable and infinite means. So what we can say, this A and n, between A and n, there exists a bijection from A to n or n to a. In any sense we can say, because bijection is a inverse mapping. Clear? Okay. So that is why the first statement is true. If A is both countable and infinite, then we can have a bijection between A and N. So it is a true statement. So what about the second one? If A is countable and some A dash subset of A we are taking, then A dash is also countable. Is this true or false? Anyone? A subset of a countable set, whether it is countable or not. Like you can have a just guess also. If we are taking a subset, true, yeah. Like subset means by induction we can say it is something less than this A, right? So obviously the bigger one is countable means obviously that smaller one will also be countable. So that is the induction behind it. Now let us see how exactly it is coming. We are getting A dash is subset of A. Okay. And also A is countable. Since A countable, we have some listing A1, A2, A3, etc. That means A1 corresponds to the natural number 1, A2 corresponding to 2, like that. So we can list the elements of A like this. Out of that, we are extracting, since A1 is subset of A, we can extract the elements. Maybe A1 can be in A dash, we don't know. Okay, not A1, it is A dash, sorry. A dash, okay. We don't know A dash, A1, small A1 can be in A dash or not. It can be or it cannot be. Maybe A2 can be or cannot be. But out of this, we are choosing. Suppose A2 is there. First I am choosing A2. Then suppose after that only A5 is there. Okay. So what we are getting is a sub collection like this. What I am doing is I am renaming A2 as something AI1 or something. Okay. I am renaming that. I am taking a subsequence, a smaller one than A. So AI1, AI2, something like that I am choosing. Okay. This I1 can be any number from 1, 2, 3, etc. Okay. After that I2 can be any number after I1. That means I1 plus 1 and so on so. Okay, clear? So like this a listing. And here also, okay, here also what I can have a bijection. AI1 can be going to 1, AI2 is going to 2, and so on so. Okay, so this kind of bijection with the n, there will be one bijection. Okay, again we got a bijection, some f dash from A dash to n. Fine. So we got a bijection from A dash to n. So what is our answer? It is also countable. Correct? Okay, one case, in case it is countable. Suppose if it is finite, in case it is denumerable. So what I have done it is, in the case of denumerable, like it is 7, 8, etc. infinitely I am going. Now, in case if A is finite, that case is actually easy. A dash is also finite because suppose A has some n elements, A dash will have some lesser elements than n. So A dash will also be finite. Okay. So this case is fine. So in both the case, A dash is countable. That means it can be either finite or countable. Okay. And okay, one more case is there. Just to be specific, what I can say is, if A dash is, sorry, if A is infinite set, okay, in that case also A dash can be finite. It need not be, suppose A is denumerable. Okay. Countable means it can be denumerable or finite. In case A is denumerable, A dash can be denumerable as I shown earlier. Okay. Or it can be finite also. Suppose I am just taking only one element from A. Okay. That I am treating as A dash. So A dash is just one element. So it is finite. Okay. Or maximum it can be denumerable A dash. So whatever the case, A dash will be countable. Okay, is that clear for everyone? So it is just like an induction only. I am just giving details so that you can understand like how the theory works. That's all. Okay, now the third option is, suppose A1, A2, etc. These are all subsets of T and these are all disjoint countable sets. That means disjoint means if I am taking the intersection A1 and A2, there is no element. A1 intersection A2 will be empty. These are all separate sets. These are all subset of T. Then the question is union of A, whether it is a countable set or not. Any answer for this third question? True. Can anyone explain also? Like because we are taking a countable union of countable set actually. Union AI means it is like a countable union. Okay. And each AI itself is a countable. So like countable sets like we are listing together. How the bijection will be possible there? If it is countable means this union AI should have a bijection with the N. Correct? Let us see how it will work. So third one is union AI or AI are countable. Since AI are countable, as I told earlier, each AI I can write like I can list them. Okay. For example, if I am taking A1, the elements of A1 I am listing as A11, A12. The first one here, 1, 1, 1, 2. That first one is corresponding to this one. Okay. A13. So like this a bijection. That means this is going to 1, this is going to 2, this is going to 3. So this forms the natural number. Okay. Like this a bijection is there for A1. In the same way A2, for A2 corresponding to 2. So the elements I am listing because all these elements are distinct from A1. We already saw these are all disjoint collection. So this is A21, A22, A23 and so on so. Fine. In the same way, the ith one I can write it as corresponding to I. I am listing the elements as AI1, AI2 and so on so. This list goes. Now I am doing a small technique here actually. Okay, I am just listing all the elements in a nice way so that I will get a bijection. A11, A12, A13, A14, etc. Let me write all the elements. So the first row correspond to the first set. A21, A22, A23, A24, etc. A31, A32, A33, A34, etc. Let me write one more row. Okay. So like this I am listing all the elements of A1, A2, A3 and so on so and this rows goes on. Now how I will list it? So what I will do is I will list the elements like this. Okay. Okay, in this way I will list it. That means this A11 is the first element. Then A21, then A12, then A31, then A22, A13 like this. So the union of AI will be like this. A11, A21, A12, A31, A22, A13, then the next diagonal. So each diagonal we will cover like that so that we can count, means we can have a proper listing of all elements of union of AI. So what exactly we will doing is, this we are associating to the natural number 1, this to 2, this to 3, like that we will get a bijection between union of AI and the natural numbers. So this is the way how we like associate the how we get the bijection between the union of AI and the set n. Actually, this kind of method we can use in so many, like later on if we are continuing in maths so many ways, like in so many places, you can see this kind of diagonalization counting like this to get a bijection from the set to n, okay, to prove the countability of some particular sets. So this is like a very standard way of counting, okay. So is that fine for everyone? Any doubt in this question? So this is also actually 3. Third option also true. 3 is also true. So whatever given in the question, all the options are correct answer. Correct. Okay. Now we will go to permutations. Permutations you have already seen what is permutation. Can anyone tell what is permutation? Permutation on some finite set.
Number of arrangements.
Number of yeah, in some sense, yeah, we can say, actually we'll say number of bijections. Okay, I mean if I am, okay, arrangements also we can say, because I am taking 1 to etc n, like in the set 1 to etc n, suppose I have a set, so 1 2 3 etc n I have. So in how many ways I can arrange all the elements, like maybe I can write 2 1 4 etc, something like that I can arrange. It should not repeat, okay, and for every element one element should be there. So that is what exactly means the bijection. Okay, so okay, bijection, and the bijection is from the same set to the same set. For example, row is from A to A and row is a bijection. So it is a, we will call it is a permutation where A is a finite set. Okay, now it is given that the set is ABCD and the permutation is given as ADBC. Okay, the question is what is the inverse? So since it is a bijection on a well defined set, so obviously it will have an inverse. What is that? Inverse means, by the way, 1 minute, inverse means row star row inverse. Here what is the star? Star operation is composition, because it is a function, bijection is a function. Okay, row is a function, row inverse is a function. So the group operation star is a composition operator. It should be equal to row inverse star row, which is equal to identity. Identity permutation means like A is going to A, B going to B, C going to C, D going to D. So if one row inverse, if one permutation satisfies this condition for row, then that permutation is called the inverse of row. So row is given here. Question is what is row inverse? You can just do the calculation in 2 minutes and let me know which option is correct. Or if you have some more doubt in the question, or in the like you are not much aware of permutation and all, or inverse or something, you can just ask me. I will explain once again. Okay, someone is telling B, so correct option is B only. Let us see how we will get the option B. Okay, so row is given as ADBC. I hope you know this kind of notations. Okay, which one you want to explain? Permutation? Which portion? Okay, permutation. So permutation basically means it is a bijection. Okay. Suppose A is any finite set. Okay. And if I have a map row from A to A such that row is a bijection. What is bijection means? It is a 1-1 map and it is a non-2 map. That means corresponding to each elements in the range, there should be a pre-image. That is the on-to-ness. And one-one-ness means distinct elements should map to distinct images. So here the domain and codomain has the same number of elements because both are A. So we are mapping the elements of A to the elements of A only. Okay, so that all elements are mapped to elements of A, and all elements of in the domain codomain A is mapped by some elements from the domain. Okay, for example 1 2 3 1 2 3, suppose this is my set A to A. So I am mapping a function f as 1 is going to 2, 2 is going to 1, 3 is going to 3. So this is 1 1 and on 2 because each distinct elements has distinct images. Okay, and all elements from this set is mapped by some elements from this set. Okay, so this is a bijection, and this bijection is from same set to same set. So we will call it a permutation. That is the definition of permutation. Okay, now I hope it is clear. Otherwise I can explain again. Please let me know. Okay, now the set A is given as A, B, C, D. So instead of this 1, 2, 3 like that, we have some set elements are A, B, C, D. And what is the row given? Row is A, D, B, C. So this is the cyclic notation of a permutation A, D, B, C. So do you know what is cyclic notation? Cyclic notation means, this exactly means A is going to D, D mapping to B, B going to C, and finally C going to A. Okay, so that is the cyclic notation means. So we can see A, B, C, D, where A is going to D, and D is going to B, D going to B, B is going to C, and C is going to A. Okay, so this is AD, DB, BC, CA. That is how the cycle is written. Okay, this cyclic notation, this is the cyclic notation of permutation. Means every permutation may not be able to write in the cyclic notation like this, but for this particular example, we can write the permutation like this. Now, the question is, what is row inverse? Okay, so what we want to find is A should go to, means row star row inverse should be equal to identity. That means if I am applying row inverse first and then row, okay, 2 times I am composing, then A should go to A, B should go to B, C should go to C, D should go to D. Okay, for example, let me tell. Here we know A is going to D. So where should this D map under row inverse? Any idea? In row it is going to, A is going to D. Then in row inverse, where should it go? It should go back to A, right? Then only 2 times. A is going to D, D is going to A. Then in the composition what we will get? A is going to A. Correct? That means A, D. Okay. So again I am writing row inverse. I just want to know where A, B, C, D are going. So that is, then I will get the inverse permutation. Okay. Here we know A is going to D. So I am saying D should go to A. D should go to A. So I am writing below D, it is here. Now B is going to C. So C should go to B. Okay. Next C is going to A. So in the inverse A should go to C. And D is going to, sorry, 1 minute. Okay, D is going to be, the last element D is going to be, so this B should go to D. This is the easy way to write it, just the reverse the process, because inversion is the reverse of the thing. Okay, Now, if you want, we can write row composite row inverse and row inverse composite row. So, what does row composite row inverse means? First, we should apply row inverse first, then row. For example, A, B, C, D. Now, in row inverse, A is going to C, right? And in row, C is going to A. So, what we got? A going to C and C going to A, because we just did the inversion. So, A is going to A. In the same way, B going to D and D going to B. So, B should go to B. B, D, B. So, final one is okay. The same way you can verify CB, BC. So, it should be and DA, AD. So, we got in the same way verify row inverse composite row also. It should also be equal to identity. Okay. So, to find the identity, it is very, to find the inverse, it is very easy. Just reverse the process. That's all. Okay. Now, okay, if row inverse, I can write it as a cyclic notation. What is this? AC, BD, CB, DA. So, A is going to C, right? A going to C. Okay, then what is C? C is going to B. C going to B. And then B is going to D. Again D is going to A. That we don't need to write because we are starting with A. So, the cycle after D, it is A. So, this is ACBD. Let me check this. Okay, this is the answer ACBD. Okay, someone already told the answer also ACBD. Is that clear to find the inverse of some given permutation? Clear for everyone? If it is not clear, please ask. We can discuss again. Otherwise, we can go to the next question. Okay. Now, the next question is, which of the following is not a group? And it is given the set with the operation. What does a group means? It is a G. What is group? Group means a set G, and in G there should be some operation star. Okay, this star is actually a function from G cross G to G. Okay, so this is the group. Group means it is like a combination of a set and a operation on the set. Clear? Now, this is a group if it satisfies some certain properties. So, let us recall what are all the properties. The first one is closure property. I am not giving the details of that since we have already covered that in the class. But closure property means if A and B are in G, then the operation, after the operation we will get A star B, that should also belongs to G. And the second one is associativity. Associativity basically means A star B star C. That means the order of the operation, so A star B star C, doesn't matter. If I am taking B star C first, then doing A star B star C, or if I am taking A star B, then I am composing with or operating with C. In both case, whatever the order, it does not matter. That is the associative property. And existence of identity. What does this mean? For any A in G, there should exist a E such that A star E star A equal to A. That means if I am operating A with some identity, some element, some particular element A, then it should give back A only after the operation. Okay, if such an element E exists, that is the identity element. And for some particular group, that identity element will always be unique. There is only one and only one identity element. Okay. Now the third option is existence. Fourth option is existence of inverse. That means A star A inverse. There should exist an inverse of A such that if I am doing the star operation A and A inverse, I should get the identity. What is the identity? This identity already defined here. So I should get the same identity and it should be equal to A inverse star A. So if G star satisfy all this property, then we call it is a group. And a abelian group means star is commutative also. What does commutative means? A star B and a B star A are equal. That means if I am taking, like if I am changing the order, then also it should be same. That means abelian. Not all groups are abelian, there are non-abelian groups also. Now we will go to the question. Okay. Okay, can you just go through the all options and tell which one is not a group? Just take some minutes and think about that, like whether all these four whatever given in the option, whether it is satisfy all the group axioms, or if it is not satisfying, which one is not satisfying, and which property is not satisfied. Go to the all options. Any answer? Or we can go by option wise. First we will go to the option A, Z3 plus 3. Can anyone tell whether this is a group or not? Question is the elements, the set which is not a group. Here first one is Z3 plus 3. Whether it is a group or not. Do you know Z3 and plus 3, like what are all this notation and all? Plus 3 means addition modulo 3. Okay, let me ask one question first. Two what is Z3? Z3 means equivalent class of modulo 3. Okay, that means if I am dividing all the integers, what are all the possible remainders I can get? Okay, if I am dividing with 3. If I am dividing with 3, either it can be a multiple of 3, or I will get a remainder 1, or I will get a remainder 2. Okay, so possible remainders are 0, 1, 2. These are actually equivalent classes of that operation. For example, in the class 0, all elements like minus 3, 3, sorry 3, 0 also 3. Because if I am dividing all these elements of class 0, I am getting the remainder 0. Okay, so this 0 actually represents the class 0, because we have seen already the equivalent classes and all. Okay, now class 1 will be all the sets, all the elements. When it is divided by 3, we will get the remainder 1. For example, 1. If I am dividing 1 with 3, the remainder is 1, right? Again, I am taking 4. 4 by 3 if I am taking, I will get remainder 1. Like this it will go. Okay. And also here it will be minus 2 and so on so. Okay. So whatever, for easiness you can just think Zn means in general, Zn will be 0, 1, 2, etc. n minus 1. And in this usually we will define the operator plus n. Okay. For example, let's go back to Z3 only. In Z3, I have element 2. What is 2 plus 3? 2. Plus 3 is the operation. What is 2 plus 2 in Z3? Any idea? Yeah, 1. Correct. Good. So, to find this kind of things, what we need is just add the things. What is 2 plus 2? 2 plus 2 is 4. Now think, what will be the remainder when 4 is divided by 3? What will be the remainder? It will be 1. So, 4 is actually belongs to the class 1. Correct? Okay. So, 2 plus 2 should be equal to 1. That is the operation addition modulo 3. In the same way, addition modulo n should be like this only. Okay, I hope the operation is clear for you. Okay, is that clear for everyone? Addition modulo 3 and set 3 group. Now we need to check whether it is a group or not. Like I have given what is the set and what is the operation. To check whether it is a group, we need to check all the 4 axioms. So let's go one by one. See, if these things are like feeling very easy for you, I can avoid this kind of explaining all this kind of things like all the axioms. And I don't know whether you are okay with that or should I explain. Means if it is very easy concept, this verifying axioms and all, just let me know. Or if you want to explain me more on this, then also let me know. We can go like that, okay? Now, what is the closure property? For that, what we need to check is, we should take 2 elements of set 3. That means all possible pairs from set 3 and add and then see whether it belongs to set 3 or not. So you can verify all those kind of possibility. So whatever we are adding and whatever we are getting, finally what we will do, we will take the remainder when divided by 3 of the sum. Okay, so the remainder can be either 0, 1 or 2. For example, if I am doing 1 plus 2, I will get actually 3, but it should be equal to 0 because 3 divided by 3 gives a remainder 0. Okay, now if I am taking 1 plus 1, it is 2 only. Okay, now again as I told, if I am going 2 plus 2, it is not 4. If you are thinking 2 plus 2 is 4 and it is not in set 3, it is wrong because we are having not usual addition, addition modulo 3. So under addition modulo 3, 2 plus 2 is actually 1. In the same way, you can verify any addition like between 2 elements and we can say closure property is satisfied. And the next one is associativity. So associativity is very easy. Like it is just like whatever it is just addition only. Okay, like if I am adding these 2 elements, then adding to other, finding remainder, or in other way also if I am adding, I mean order actually doesn't matter, correct? Okay, associativity you can verify, take all possibilities of 3 elements, then try A plus A, B, C. I am just giving the notation equal to A plus B plus C. This actually like from the property of usual addition, it holds. Now, identity. Can anyone say what is the identity in this group? Identity is an element 0, correct. 0 is the identity. What is the reason? If I am taking any element, say 1 or 2 or 0, whatever, if I am adding with 0, I am getting the same element, correct? 0 plus 0 equal to 0, 1 plus 0 equal to 1, 2 plus 0 equal to 2. Okay, so this is the property of identity. If I am adding that with like left adding, right adding, whatever, I should get the same element. So 0 is the identity. So existence of identity is also done. Now the thing is inverse. 0 is the identity. So just leave about the 0 case now. Okay. First you tell me what are the inverse of 1 and 2. What is the inverse of 1? Yeah. What is the inverse of 1? For 1, I should have an inverse, okay, such that under addition modulo 3, if I am adding 1 and that element, I should get the element 0. Okay. If I am adding 1 with 1, I will get 2. If I am adding 0 with 1, I will get 1. So the remaining possibility is 2. So what is 1 plus 2? 1 plus 2 is 3. That means it is 0 in addition modulo 3. In the same way, inverse of 1 is 2. And what is inverse of 2? So the same equation we can use. With 2 I am adding 1. Yeah, I am getting 0 under addition modulo 3. Okay, so inverse of 2 is 1. Inverse of 1 is 2, inverse of 2 is 1. Okay, so we have 3 elements 0, 1, 2. Inverse of 1 is 2, inverse of 2 is 1. What is the inverse of 0? Yeah, it is 0. Inverse of 0, because 0 plus 0 is 0. Okay, that is the condition. Otherwise also in any group for like identity element, that itself will be the inverse for that. Okay. Now the second option is Q under multiplication. Can you say what about Q under multiplication? Whether it is a group or not. So we need to check again these 4 properties. Okay, closure property, associativity. Associativity and all actually easily holds. You can just like to think about that. And this identity inverse. So is this a group or not? Option 2. Anyone can answer. Someone is saying it is a group. Or is this an earlier message? Okay. First let us see. Q with the multiplication. Okay. Q with the multiplication means first thing is closure property. That's very easy. If I am taking A, B, Q means rational numbers. Okay. Q notation is for rational number. A and B are rational number. I am just taking the product of two rational numbers. Obviously, it will be a rational number. Okay. Okay. Before proceeding further, let me take R minus Q. Okay, that means irrational number. Does it have closure property? I am just asking the question. Does it have closure property? I told if A and B are rational numbers, A dot B is also a rational number. Now, if I am taking the two irrational numbers, I can ask the question whether it is a group. So, first of all, let's start with the very simple thing. Whether the irrational numbers has the closure property. If I am taking two irrational, yeah, no. Can you tell any example, reason? If it is no, we should have some counter example like product of irrational number is not irrational, correct? Any idea? Okay. For example, consider root 2. Root 2, it is irrational, but its product is 2. It is a rational number. Okay. So the answer is no. So that's about irrational. Okay, leave that. Let's come back to the Q case. Under multiplication, we have seen that this is closed under multiplication. Now the second option is associativity. It is just usual multiplication. We know like whatever the order we are multiplying, it is not going to be an issue. So it will be associative. That is not a problem. Now, what about identity? Can anyone say what is the identity of Q under multiplication? Addition, we know what is identity. 0, it is the identity. Yeah. Under multiplication, identity will be 1. Because I am taking any Q, rational numbers in Q. Q dot 1 will be Q. Whatever the rational number I am taking, it will be same as 1 dot Q. Okay, that's all about identity. Now, what about the inverse? If Q is a rational number, what is Q inverse? Anyone? That means I should multiply Q with some particular element so that I should get the identity 1. We got identity is 1. Okay. We are saying it is 1 by q. But here actually we have something wrong. We cannot tell like this. Now, I told q is a rational number. Q can be any rational number. It can be 0 also. If q equal to 0, then what we will do? Whether 1 by 0 exists? So that 0 into 1 by 0 equal to 1, can we write like that? Okay, for any, for any non-zero rational number, we can say the inverse of q is 1 by q. So that q into 1 by q will become 1 and okay, solved. But in case q equal to 0, whatever with 0, whatever I am multiplying here, I will get a 0 only. I am not getting 1. Yeah, not getting 1. That means for 0, inverse does not exist. What does that mean? It is not a group. Because if it is group, for every element there should exist a inverse. But for 0, no inverse. Okay. So it is not a group. Even though we got all other properties satisfied, even for inverse also we will doubt that, okay, for q 1 by q is there. But for 0 is the only problem actually. Since because it is the problem, we cannot say it is a group. So it is not a group. Now again, the next one. Okay. Now we are taking, going a bit extended because in Q 0 makes a problem. And so Q minus 0 can be a group. Just check about that. Q minus 0. Okay. Check Q minus 0 with the multiplication, a group or not. Okay, this just verify that. Okay. Now again let's go to one extended. We are taking r minus 0. That means rational, irrational, everything together, real number. I am under multiplication we got for 0 some problem is there. So we are removing the 0 from here. So we got r minus 0 with the multiplication. Third one is r minus 0 with the operation multiplication. Whether it is a group or not. Can anyone tell now whether it is a group or not? Again, it's like easy because, yeah, it's a group. It's easy because we have seen that closure property. Closure property, if I am taking the product of two real number, it is again a real number. So associativity means whatever the order I am multiplying, it will not be a problem because I will get the equal value on both LHS and RHS. And identity, again under multiplication, it is 1. And what about inverse? Inverse also, it is in the same way. For any real number r, 1 by r is the inverse. Okay, and here 1 by r is not a problem because from r we have removed the 0 element. Correct? So 1 by 0, that thing like not going to concern us. So this is a group. Now let us very quickly go through the fourth one also. 2z plus. Any idea what is 2z? Is abelian group. Okay. Okay, leave about abelian now. Yeah, even integers. Okay. Yeah, I was just asking what is the group. Obviously, it will be abelian because under addition, a plus b and b plus a are same. So 2z plus means 2z means like taking all the even integers. That means minus 4, minus 2, 0, 2, 4, etc. Here also it is very easy to verify. Closure property means if I am taking two elements, okay, it will be in the form 2m and 2n, something like this. All are even numbers. So it will be equal to 2 into n plus n. Correct? So it will belongs to 2z. Okay, so closure property is easily satisfied, and associativity also. Under addition, you don't need to check much about associativity. It will hold very quickly. And what about the identity? What is the identity here? Yeah, 0 is the identity. Usually in addition, always like 0 will be the identity. Okay, like if I am adding any element with a 0, I will get the same element. That's all. The same way, what is the inverse of some 2n? What is the inverse under addition? It will be minus 2n, right? The opposite, like negative part, because 2n plus minus 2n, yeah, minus 2n. It will be equal to 0, the identity. So this is also a group. So out of the 4 options, the one which is not a group is Q with multiplication. All others are we got as group. Now the option is a binary operation. Binary operation is actually nothing. No need to think about group and all. It is just an operation like that associated with 2 elements. That means some star is there means star from Z cross Z to Z as star of AB. Usually we will denote it as A star B. Star is actually a function from Z cross Z to Z. Okay. Star of AB we will define as A star B. Usually we will take star as either addition or multiplication or composition, something like that. Here they have defined how x star y is defined. For example, okay, let me write the same notation. X star y. X star y is given as 1 plus 12x plus xy. This is the definition of the binary operation star given in the question. So the question is, what is 2 star 3? Yeah, very good, 31. So it is a just a calculation only. What is 2 star 3? Just understand what is the star operation. Okay, 2 star 3 means here instead of x we have 2 and in place of y we have 3. So just replace this equation 1 with x and y as 2 and 3. Okay, 1 plus 12 into 2 plus 2 into 3. So you can just do the calculation and we will get the answer as 31, and it is our option A. Okay, I hope it is clear for everyone. Please let me know if some doubt is there. Okay. Now again we are going to the complex cube root of unity, and the question is what is the inverse of omega square in the multiplicative group 1 omega omega square. So the group is actually 1 omega omega square with the omega. Okay, good. With the operation usual multiplication. Okay. Now I don't know whether you all know about the complex cube root of unity and all. So let me just give a simple explanation about that. Okay. So if we are having the equation x cube equal to 1, okay, then it is a third degree polynomial. So for any n degree polynomial we will have n roots or n solutions. So this solution, this equation x cube will have 3 solutions. So what are all the solutions? That solutions are usually denoted by 1 omega omega square. That means for 1 it is easy, you know, 1 cube equal to 1. Okay. In the same way, this is actually omega and omega square are complex numbers. You may not be much aware of those things, but just understand this, that is the notation for that particular complex number. So omega cube will also equal to 1. Omega square cube will also be equal to 1. Okay. And geometrically saying how this will be distributed. So if it is a unit circle with center 0, radius 1, this is the circle 0, center 0 and radius 1. Okay, where does the 1 comes? 1 is this point, correct? 1 means this one. Okay, the first root 1 is this one. Where this omega and omega square are placed? Omega will be somewhere here, omega square will be somewhere here, so that this actually divides the whole circle into 3 equal parts. That means this total circle is actually angle is 360 degree. So each of this will be 120, 120, 120 like this. Okay, so if we are dividing like this and drawing like this, so whatever we are getting here, this point is omega and this point is omega square. This is in the case of cube root. In the same way, nth root also you can do. Just leave about those things. So this is the this under multiplication is a group. First verify it is a group. Okay, and this you can do as a homework. Now this is the same like repetition of the earlier question.
Madam, could you please explain this diagram again? Like, I just missed a few. I
Okay.
think I have solved it wrong in the assignment.
Yeah. So what I am saying is we have the group 1 omega omega square with the multiplication. So I am just giving what exactly is the group. So this 1 omega omega square means what are exactly the elements. Okay. These three are the cube roots of unity. Cube roots of unity means solution of the equation x cube equal to 1. Since it is a third degree equation, it will have 3 solutions. So that 3 solutions are 1 omega and omega square. And these, where these 1 omega omega square are placed in the plane, complex plane. Actually, omega and omega square are pure complex numbers. Okay. That is what the diagram says. Usually in any case, it is not about cube root, any nth root also, we can see where the roots are placed. Okay, first we will start with 1. We know the position of 1. Okay, now total we have 360 degree here. Okay, since it is cube root, we will divide 360 by 3 and this is 120. Okay, so we will take the angle first 120 here. This is our first 120. Again next 120 here. Okay, somewhere here it will come, and the remaining will also be 120 because 3 120 equal to 360. Okay, so whatever the point here, if we are drawing this kind of line, then whatever the point it is omega, and whatever coming here it is actually this maybe this angle and this angle are same, like my figure is not that good, but I hope you understood. These are all equally placed, distance between 1 omega 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 square 1. These are equally placed. So this is our elements 1 omega and omega square. So you can easily see, like now you know the position, so you can just see what is the complex representation, like omega equal to a plus I, something you can write, right? So just check that also if you are interested. How this omega is just a notation. How this like what is the exact value of omega and omega square, then you can verify later. So I hope that is clear. Now we got group 1 omega omega square and dot, and again verify it is a group by checking all the 4 properties. Okay.
Madam, I'm so sorry to interrupt again.
Yeah.
Like, this is actually my first problem solving session for this subject. I missed the other problem solving session. So, where can I access? Like, is there any recording? Like, there are transcripts and videos are there for the course, but are there any like recordings of these?
Yes. Recordings are there. Like both session we are recording and uploading in the YouTube. So in your portal there is a like week 1, week 2 like that it is there.
Yeah, yeah, yeah.
Yeah, below that problem solving session, one tab is there. Go to that, it will lead to an Excel sheet. So there you can get the all YouTube links of our recordings, and also the
Okay.
drive link of the this PDF. Okay, we will upload PDF also in there.
Because the videos are there in itself for the courseware. The YouTube videos are there. And I was curious about because I didn't know initially that there is a session like this. After I checked my inbox, I realized that I have missed the session.
Yeah, actually this is just second week only, so you missed maybe like maybe 3 session, like week 1 2 session and week 2 1 session. So you can
Okay.
join like both session like as per your time. The thing is, whatever you missed, it is available in the YouTube. Just see it
Okay.
in there. Yeah,
Okay. Thank you, ma'am.
yeah. Okay, then let's proceed. So the question was, what is the inverse of omega square in the multiplicative group? So the inverse means omega square into something. Okay, what will be the identity here? To know about the inverse, first we should know the identity. Yeah, identity is 1. So in multiplication it is like just an easy thing. 1 into 1. 1 into 1 is 1. Omega into 1 is omega. Omega square into 1 is omega square. This is usual multiplication of complex numbers. Okay. So we got 1 as the identity. Okay. Now we can see what is inverse. We need to find the inverse of omega square. So suppose this is our inverse element. Then omega square into that inverse element should be equal to 1. Okay, someone already told it is omega. Okay, now I don't know whether other understood those things also. I will explain. What they told is omega square into omega equal to 1. So what does this means? Omega cube equal to 1. So this is where we are starting, right? What we are starting? This 1 omega square are solutions of x cube equal to 1. So 1 cube equal to 1, omega cube equal to 1, omega square cube equal to 1. Correct? So we got omega cube equal to 1. This is same as omega square into omega equal to 1. This is same as omega into omega square equal to 1. Correct? So inverse of omega square is omega. So in the other way, what is the inverse of omega? What is the inverse of omega? Omega square. Okay, good. The same thing, like if A has inverse B, obviously B has inverse A also. Okay, that it is like you can remember that. Fine. Okay, now this question actually includes like I don't know whether you know all the groups defined here. I will just give like some small idea about each of the groups here. So maybe in the like maybe week 3 and onwards you will learn more about this. Anyhow, let me give. Do you know what is plain for group? We will notate it as V. The question is, what are all like among all these four? What are all the abelian groups? Abelian means commutativity. That means A star B and B star A are same. Okay. Now we will see Klein for group and set for plus 4. In Klein for group we have 4 elements and in set for plus 4 also we have 4 elements. Okay. So the operation star, okay, this is a kind of group table. We can write the group table like this. Before that, let me give the group table of Z4 plus 4. This is Klein for group. We will come to that it after Z4 plus 4. Z4 under addition modulo 4. So this is our operation addition modulo 4. We will write it here and we will list all the elements of Z4. 0, 1, 2, 3. Okay, that means if I am dividing all the integers with 4, what are all the possible remainders? That is 0, 1, 2, 3. 0, 1, 2, 3. Now the operation is, what we will get is 0 plus 0 under addition modulo 4. So that thing we will write here. 0 plus 0 is 0. Okay. Then what is 0 plus 1? 1. Okay, 0 is the identity. You might have already understood that now. And 0 plus 2 is 2. 0 plus 3 is 3. Okay. In the same way, 1 plus 0 is 1. 1 plus 1 is 2. And what is 1 plus 2? Anyone?
1.
1 plus 2. 3. Yeah. 1 plus 2 means first you do the usual addition 1 plus 2. Okay.
Oh, I'm considering that. Oh, so sorry.
Okay. Yeah, 1 plus 2 you will do and you will get a 3. 3 is already in set 4. So we can write it like that only. But what about 1 plus 3? Yeah, 1 plus 3 is 0 because 1 plus 3 is under usual addition it is 4. But here operation is plus 4. Okay. Yeah, operation is plus 4. So what we will get is 0. Okay.
Madam, I'm getting a little confused again. Like, I said 1 plus 2, 1 previously. Like, in this answer, it is 1 plus 3, it is 0 for this modal plus 4. Can you just, like, I'm just unable to, just join the dots a little bit.
Okay, okay. Now you want me to explain once again?
A little bit. I'm just getting a bit confused. That's all.
Okay, okay, fine, fine. I'll explain. So what I am asking is 1 plus 2 addition modulo 4. Okay, Z4 plus 4. So the thing is, first if we are having whatever addition modulo n, we will just do the addition 1 plus 2, usual addition, it is 3. Okay, now check whether this 3 is there in our set Z4. Z4 will be, let me write Z4 is 0, 1, 2, 3. Correct? The remainders of under
Yeah.
the like division. Okay. So 1 plus 2 is 3. 3 is there in set 4. So we can write it like that only. Now I am coming to 1 plus 3. What is 1 plus 3 in usual addition? It is 4. But 4 is not there in set 4. Correct? Now if I am dividing 4 with 4, what remainder I am getting? It is 0. So I am replacing this 4 with 0. Here also we are doing the same procedure. We got 3 under usual addition. So I am dividing 3 with 4. The remainder is 3, right? Okay. The same thing we are doing for all operation. We will add whatever the addition we are getting, divide it with 4 and the remainder we will write. That is the, like, under that operation, that is the value. Is that okay?
Okay, okay. Now it's clear.
Okay. Now in the same way, 2 plus 0 will be 2. 2 plus 1 will be 3. And 2 plus 2 is 4. 4 means remainder is 0. And what is 2 plus 3? Anyone? Plus 3?
1.
Yeah, very good. Because 2 plus 3 is 5. 5, if we are dividing with 4, the remainder is 1. So in the same way, 3 0 is 3. 3 plus 1 is 4. Sorry, 4 means 0. And 3 plus 2. 3 plus 3. 3 plus 3?
2.
Yeah, 2. 3 plus 3 means 6. So yeah, very good. Like while taking the modulo 4, we will get 2. So okay, why I have written Z4 plus 4 is, it is like easy example for you. And this is how we write, like if it is some symbol group or something, this is the way we write the group table. So from this actually, you can easily see whether it is abelian or not. Okay, what does abelian means? A plus B and B plus A are same. So if I am taking, see, 0 plus 2 means this element will come. Okay, this is 0, this is 2. So this is 0 plus 2. Okay, now 2 plus 0 means 2 and 0. The common point is here. Okay, so 0 plus 2 is 2, 2 plus 0 is 2. So that means, see, this whatever I have written in this table, it is a kind of symmetric. Okay, that means it is abelian. whatever the element you are taking, yeah, it is an abelian group. A plus b, b plus a, both are same. Okay, usually it is in almost in addition, it will follow the abelian. Okay, means it will be commutative, like addition, multiplication and all. So this is the example set for plus 4. Now this actually again I am defining Klein for group. This is different from set for plus 4. For that I have an operation star. Okay, actually what is this star and what exactly is this group and what is the exact difference between Klein for group and set for, these things we will see in the upcoming lectures. So before that, let me just introduce how this star is defined. So using this like table notation only, I can like properly define the star. Means I am defining A star B for all A and B in the group. Okay. So it will be, here E is the identity. So E multiplying with any element will give the same element. In the same way, here also AE, BE, CE. Okay, this is also an abelian group only. Okay, after writing we can see. Now, the next thing is for Klein for group. For any element A, the inverse is itself. That means A star A will be identity, B star B will be identity, C star C will be identity. Okay, so we can fill along this diagonal E. Okay. Now the next one is, okay, this is CB, this also CB, and this is A. Okay, this is the group structure of the Klein for group. So maybe first row, first column is CC, diagonally CC. Here also it is like, you can remember what exactly the Klein for group. Okay, here also it is a kind of symmetric only, means along row, like you know symmetric method, right? If I am changing rows, columns, then also it will become same. Okay, so from this you can consider, see, A star B, A star B is C. Okay, A star B is C, and B star A, B star A is also C. Okay, in the same way you can do all the like commutativity, you can check, and what you can see it is a abelian group. This is abelian, Z4 is also abelian. Now it is symmetric group S3 and dihedral group D4. Before going to S3 and D4, let me just give an explanation of Sn and Dn. Okay, for all n. Do you know what is Sn? Anyone? Sn? Sn we will say symmetric group on n letters. Okay, so what exactly means is we will take the set 1, 2, 3 etc. n. Okay, and consider all the permutations. Say f permutations. Let me say it is rho. Usually we will denote rho sigma like that for permutation. That means it is a bijective mapping from the same set of n letters. Okay. Okay, such that rho is bijection. That means this is our Sn, or it is set of all permutations. So whatever I have written in the set notation, it is the definition of permutation also. Okay. Okay. So this is the this is the group. And what is the group operation here? Can you guess what will be the group operation? We already seen like many group operation, addition, multiplication, like some star and all. In this set Sn, we should have an operation so that it will become a group. It is a group. that we can verify. So for that to become a group, we should have a valid operation between the elements of Sn. So the composition, it is see, if you are noticing, the elements of Sn are functions actually. It is not like some real number, integer or something. These are all functions from one set to another set. Okay. So in function, usually what operation we will do? The composition operation, F composite G, that one. Okay. So rho star sigma, say, will be rho composite sigma. Okay, this is the group operation star here. Now, okay. Now the thing is, we can very easily verify it is a group. So one thing we need to check is closure. Rho star sigma belongs to Sn. This is easy because rho is a bijection and sigma is a bijection on n letters. So its composition is also a bijection. Rho composite sigma also belongs to Sn. And the associativity. For any function, any three function, it satisfies the associativity. These are all the basic things. If you want, you can verify. Like to verify that F composite G composite H of x equal to F composite G composite H of x for all x. So this is what mean by associativity. So if this condition is true for all x, it is associativity. So this is a very easy thing to verify. Just do it yourself if you want more clarification on this, or otherwise if you are okay, like okay with this thing, leave it. And what about the identity? Can you say what will be the identity element in this? Existence of identity we need. We have the set of all permutations, that means set of all functions, bijective functions from the set 1 to etc. into 1 to etc. in a. What we need is what is the identity, so that if I am taking rho composite I, it should be equal to I composite rho and it should be equal to the rho. What will be the identity in functions? The identity function, you may know that, right? Identity function means 1 going to 1, 2 going to 2, 3 going to 3. So this actually doesn't matter. Like whatever the row, here I is 1 going to 1, 2 going to 2, like that. So finally if we are doing the composition with I, we are getting the same row back. Okay, that is row composite I of x. What will be is row of I of x. What is I of x? Identity of x. It is x only. That is row of x. So row composite I is row only. Okay, that is why I is the identity. Now since it is a bijection, for any row there exists a inverse, because row is a bijection, that is it is both 1 1 and on 2. So the usual way, like for example, if it is 1 2 3 3 1 2, something like this, as I have like in the first or second example we have seen that we can just reverse the things to get the inverse. Okay, so that is the inverse of the given bijection. Okay, so these are all the properties of the group. So the Sn satisfy all the group property. So Sn is a group. Okay, now I will quickly explain what is. I hope it is clear. If you have doubt, you can ask. Otherwise, I will just explain the Dn also. Okay, before Dn, I will just tell what is An, because in the assignment question, I think one An is there. Okay. An means set of all even permutations. Okay, like in Sn we got all the permutation. Out of that permutation we will collect all the even permutations to get the group An. Okay, now I am not going to explain much on this group An. I will just tell some elements that belongs to An. For example, I am just taking the element 1 2. Suppose my set is 1, 2, 3, 4. Okay. Now I am taking the element 1, 2. Is this a even permutation? Anyone? No, because okay, I don't know whether you know even permutation. Okay, before that, do you not? Okay, transposition I think already covered. Transposition is a cycle of length 2. Okay, like cycle is an element something like that 1, 2, 4, 3. I mean I can write it like this as a cycle. 1 is going to 2, 2 to 4, 4 to 3, 3 to 1. Okay, this is a cycle actually. Or I can just write to 1, 4. Okay, so these are all the cycles. So if I have like some permutation in this form, what I will write is this is same as 1, 3, 1, 4, 1, 2, and this is just 1, 4 only. Okay, so here cycle of length 2 is called transposition. That means here we have 3 transposition. Okay, since there are 3 transposition, that 3 is odd number, so it is not an even permutation, it is an odd permutation. That's all. Okay, we will get a permutation in the form of product of transposition, and we will check the number of transposition. Okay, if the number of transposition is even, then it is an even permutation, and if the number of transposition is odd, it is a, here also it is a odd permutation. Now for example, I am taking 1, 4, 3. This I can write it as 1, 3, 1, 4. Okay, so this is an even permutation. So what AN means, set of all these kind of even permutation. Take an permutation, write it as the product of transposition like this. Okay, and then count the number of transposition involved in that, and if that is even, then it is an even permutation and it belongs to AN. If it is odd, it does not belong to AN. That's all. So that is the definition of AN. Now we will go to DN also. DN is the nth dihedral group. We can see it as in a like geometric way. For example, I will give D3 and D4. So D3 means we have 3 elements. Okay, 3 elements means we will consider a triangle. Okay, triangle. Suppose this is 1, this is 2, this is 3. The elements of D3 involves all rotation and reflection. So what is the rotation? Rotation means one is going to do, it is rotating this triangle to like this. Okay, one time rotating. So 1 will go to 2 and this 2 will go to 3, 3 will go to 1. So in that way we will have 3 kind of rotation. Okay, 3 rotations will be there. And also 3 reflections will be there. Okay, so what the reflection means is, along this one we will reflect it. That means 1 is fixed there, 1 is going to 1 only, and this 2 is going to 3 and 3 is going to 2, because the reflection you can see, imagine 2 going to 3, 3 is going to 2. Okay, that is a reflection. Fine, that is the T3 element. So these 6 elements. Okay, before going to that, in Sn I told how many elements will be there in Sn? Any idea? Sn I told set of all permutation, set of all bijective mapping from a set of n elements to a set of n elements. How many elements will be in Sn? Cardinality of Sn? Any idea? Like the question is how many bijections? Yeah, n factorial. Very good. Because for example, what I am saying is 1, 2, 3, etc. We have n elements. Okay. Then what to where one can map? It can map to 1, it can map to 2, 3, up to n. Any possibilities there. So here we have n possibility. Correct? So one possibility is gone. So 2 can be mapped to remaining n minus 1 possibility. Okay, like that 3 can be mapped to remaining n minus 3 possibility, and n can be mapped to the last one possibility. So all possibility means n factorial, n into n minus 1 etc. 1. So Sn is a group with cardinality n factorial. In the same way, Dn will be the group with cardinality 2n. Okay. Here also we can see 6 map, 6 rotation and 3 reflections will be there. Now we will just see D4 also. D4 means the sides are 4. That means we will take a 4-sided square. Yeah, any question? So here also we will see since it is 4-sided, we have 4 rotations. Okay, if I am writing it as 1, 2, 3, 4. 1 going to 2, 2 going to 3, 3 going to 4, 4 going to 1. In the same way, like one time rotating, I will get like this. Okay, so 4 rotation, 4 kind of rotation I will have, and that is 1, and I will have reflection like this along this way, that is 1 to 2, 2 to 1, 4 to 3, 3 to 4. The same way along this 2, 3 and 1, 4. Okay, interchange. The same way along this diagonal, that means 1 and 3 are fixed, 2 and 4 are exchanging, and this also. Okay. Oh, sorry, presentation not visible. 1 minute, I will give me 1 minute. No, okay. Now it's visible, right? Okay. Till where it was not visible? I mean, from where should I explain again? Or can I continue just like this? Okay, I hope it is fine. So what I was saying is for D4, we have 4 rotation and 4 kind of reflections. So total 8 elements, 2 into 4, 8 elements will be there. So that is the nth dihedral group. Okay, now we will go to the question. I have explained all the groups here, correct? All the 4 groups I have explained. Okay, reflection, okay, okay, I will explain the reflection in D4. So let me draw this one. If I am taking this red line, okay, through the middle of the square, if I am taking that along that one reflection, that means if I am taking a mirror there, what will happen? 1 will go to 2 and 2 will go to 1, and 4 will go to 3, 3 will go to 4, right? So that is our map. 1 is going to 2, 2 is going to 1, 3 going to 4, 4 going to 1. Okay, that method. That is the reflection method. In the same way, if reflection is along this diagonal, okay, in that case, what we are doing, along diagonal we are keeping a mirror. So 4 going to 2 and 2 going to 4. Where 1 will go? It will not go. It is that corner point. That will stay there only. 1 going to 1 only, 3 going to 1 only. Same way, if I am taking this one, 2 and 4 are fixed there, but 1 and 3 will be exchanged. Okay, like that the fourth one is this one. 1, 4 exchanged, 2, 3 exchanged. Okay, this is the reflection maps. So I am just like giving, since it is in the question, I should explain what exactly is D4 and D3, I mean D8. Okay, so in the same way, okay, let me tell that also. Dn is the dihedral group on n letters, or what I can say is n gun, like we will tell triangle for 3, square for 4 and pentagon for 5, like that for n dimensional n gun we will take, and for that all the rotation plus all the reflections, that is the nth dihedral group Dn. Okay, so you don't need more than that, just like understand that thing only. Now we will see, I hope it is clear. Then we will see which are all the abelian group. So we have already seen Klein 4 group is abelian. In the beginning I told. and Z4 plus 4 is also abelian. Okay, using that group operation we have seen. Now let's see symmetric group and dihedral group. This is actually a functions, means it contains permutations and the operation is composition. So abelian means A star B equal to B star A. That means F composite G equal to G composite F. So the basic question is whether this composition operation is commutative. Okay, function composition. So what can you say about that? Symmetric group S3 is abelian or not? This same as asking whether the composition is uh, like commutative or not. What do you think? I mean, in general, what do you think? It will be abelian or not? Any idea? No. Yeah. Usually, function composition is not commutative. Okay. Usually, whatever the function f composite g and g composite f are different, but it is associative. Okay, usually it will be associative, that is why it is a group first of all. And for that, so our intuition is this S and Dn, since these are all function spaces, its composition will not be commutative, and so what we can tell, this need not be abelian. For that we should give one counter example to show it is not abelian. Okay, so we are, the question is S3 and D3, correct? Yeah, S3 and D4. Okay. I will give S3 one first. Okay. In S3 I am considering 1 2 and 1 3. Okay. So 1 2 is a permutation, 1 3 is also a permutation. That means 1 going to 2, 2 going to 1, 3 going to 3. And 1 going to 3, 3 going to 1, 2 going to 2. Now we are taking the composition. Composition means F composite G means first we should take the G. Okay, F composite G of X means first we will take a G of X and to that one we will apply F. So first thing to apply is the second one. So here also first we should apply this one, second one. Okay, so first 1 is going to 3 and 3 is going to, yeah, 3 is going to 3, right? 1 3. Okay, 1 is going to 3 and 3 is going to 3. So 1 is going to 3 in composition method and 2 is going to 2, then 2 is going to 1. That means in composition 2 2 1, 2 is going to 1, and then 3 is going to 1 and 1 is going to 3. So it is 3 2. So what we can write, it is 1 going to 3 going to 2. So this is the cycle 1 3 2. Now what about 1 3 and 1 2? Okay, again 1 is going to 3, 3 is going to 1, 2 is going to 2. That is our map 1 3, 1 2 2 1 3 3. This is our map 1 2. So I am taking the reverse way. First I have found 1 2 to 1 3. Now I am finding 1 3 1 2. So again in composition what we need is first we should consider this one. 1 going to 2, 2 going to 2, correct? 1 2 2 2. So composition is 1 to 2. 2 to 1 and 1 to 3. 2 to 3. 3 to 3, 3 to 1. So 3 to 1. So this is 1 2 3. Correct? 1 2 3. So this is different from the earlier one. So if I am taking 1 2 1 3 and 1 3 1 2, these two are different. So it is not an abelian group, not an abelian group. Okay. Now let me just give What is 1, 2? 1, 2 means 1 going to 2, 2 going to 1 and 3 is fixed. So it is the reflection like this. Okay, 3 fixed, 1 going to 2, 2 going to 1. So it is an element of D3 also. Okay, 1, 2 is an element of D3 also. In the same way, 1, 3 means, okay, 1 is going to 3, 3 is going to 1, 2 fixed. So this is 1, 3. This is also an element of D3. So from the same example we can say D3 is also not abelian, because we already proved 1, 2, 1, 3 and 1, 3, 1, 2 are different, correct? So from this D3 is also not an abelian. So the same way for D4 also, okay, that I will give you, like if you have understood all the concept, D4 is not abelian. Just verify this whether it is abelian or not. Okay, just you try as a homework, because it is just like the same as the earlier cases. Try uh, find two functions which composition like f composite g and g composite f are different. It is not that difficult. So you do it for yourself. Okay. So that is all about that, like symmetry group, dihedral group and all. Now more about this thing you will learn in like upcoming weeks also. So now we will just go to the, okay, in the last week we have covered like something related to relations and all. So the question is, if cardinality of A is m, then the number of relations on A is what? 2 power n, that is the number of power sets, right? Usually, what is the relation means? Relation is a function from, like is a subset of A cross A, correct? What is the relation? Relation means A or B, something like that. That means A and B are related. So it belongs to A cross B actually. So if I am having some relation, this relation is actually a subset of A cross B. Okay, any relation is a subset of A cross B. Now, the question is how many number of relations, how many relations are there? That exactly means how many subsets are there for A cross A, because here the question is number of relations on A. So instead of B, we are having A only, correct? Relation on A. So how many subsets are there for A cross A? That is the exact question. How many relation means every relation is a subset of A cross A. Okay. So and every subset we can see as a relation also. It is just an association between some elements, like whatever. It need not be an equivalence relation or something. Any relation means like even phi subset of A cross A also a relation. That means it is unrelated. All elements of A are unrelated. Okay. So how many subsets are there for A cross A? What is the cardinality of A cross A? How many elements are there in A cross A? A has m elements. A has cardinality m. A cross A means, what is A cross A? A cross A means set of whole AB such that A and B in A. So here also varies elements from A. Here also varies elements from A. So how many possibilities will be there? Here we have m possibility. In B position also we have m possibility, correct? Okay. So total how many elements will be there in A cross A? Is that clear for everyone? Like what I am saying? A is a set with the m elements. A cross A means set of all possible combination AB. Okay. AB varies from element A. For A, we have m possibility, A1, A2, etc. Am. So the same m possibilities we have for B also. With the A1 we can take A1, A2, A1, A3, A1, A4 like that. Okay. In the same way A2, A1, A2, A3, A2, 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 A3 like that. So here m possibility, here m possibility. Total m into m possibilities are there for A cross A. So cardinality of A cross A is m square. Correct. Now what is a relation? Relation is A is related to B means it is a subset of A cross B. Here A and B are same. So relation is a subset of A cross A. Okay. So how many relations are there? Means how many relations? So this question is equivalent to how many subset, because each subset is a relation, each relation is a subset of A cross A. Okay. How many relation? Sorry, how many subsets? Okay. So for a set of cardinality n, okay, what is the number of subset or like the number of elements in the power set? It is 2 power n. Here A cross A has m square elements. So this is equal to 2 power m square. So the option A is the correct answer. Is that clear for everyone? How we are getting the 2 power m square? So yeah, this is the number of elements, number of relations in the set A cross A. Okay. Now this is a same comparatively easy question. Row 1 is given as 1, 2, 3 and row 2 is given as 4, 2, 3 on the set A, 2 permutation on the set A 1, 2, 3, 4. Okay. So row 1 is, let me write 1, 2, 3. That means 1 is going to 2, 2 going to 3, 3 going to 2. And to where 4 is going, can anyone tell? Because it is in the set 1, 2, 3, 4. Question it is given on the set 1, 2, 3, 4. For 1, 2, 3, we know it is a cycle. 1 to 2, 2 to 3, 3 to 1. And 4 should go to where? 4 is not defined in the row 1 here. But we should know to where 4 is going, correct? Whatever not defined here, it is actually going to the same element. 4 should go to 4 only. Since it is a bijection, see here 2, oh sorry, this is 1, 2, 3, 1, all are covered. It is bijection means 4 should also be in the image, correct? So that 4 is the image of 4 itself. In the same way, what is row 2? It is 4, 2, 3. So 4, 2, 3 means 4 is going to 2 and 2 is going to 3 and 3 is going to 4. To where 1 is going, the only remaining value is 1. It should go to 1. So if something is defined in the like as a cycle or something, just write it in the way, and for whatever the remaining element, take it as the element itself. That is the like identity. 1 is going to 1 only, like that. Okay. So the question is just like composition. Row 1, composite, row 2. I just want you to tell this one because we have done so many questions like this. Now we know the set is 1, 2, 3, 4. Now we want to find the image of 1, 2, 3, 4 under the function row 1 composite row 2. So composite means the second function row 2 we should take. So we should check under row 2 where 1 is going. Okay. And wherever it is going, find the image of that under row 1. Okay, first apply row 2, then row 1. So can you tell what is the image of 1 in row 1 composite row 2? Anyone? Yeah, 2. Because 1 is going to 1 and then that 1 is going to 2 in row 1, correct? So it is 2. And what about 2? 2, we can very quickly, you can tell now. Yeah, 2 is going to 1 and 3. Yeah, 3 is going to 4 and 4, yes, 3. So 2, 1, 4, 3. So we can write in cycle notation 1 going to 2 and 2 going to 1 and 3 going to 4, 4 going to. Like this also we can write it. So the option is 1, 2, 2, and 3, 4, 4. Option A. Okay. This is the correct answer. Clear? That is simple question. Okay. Now the question is on 1, 1 ontoness. Function is defined as from R plus to R. Okay. Whether this is 1, 1 or onto. That is the question. Okay. So 1, 1 we know, like for a distinct element there should be distinct images. Or how we can write it is 1, 1 means f of x1 equal to f of x2 implies x1 equal to x2. Okay, this is the one condition we can check the 1, 1's. Or if x1, x2 are distinct element, then the corresponding image f of x1 and f of x2 are distinct. So this is actually the contrapositive statement of the first one. So both are equivalent statement. So when I am writing the opposite way, x1 not equal to x2 implies f of x1 not equal to f of x2. We are taking the negation in the reverse direction of the first statement. Okay. So can anyone have a guess whether it is 1, 1 or not? Just like 1, 1 we will check first. Yes or no? 1, 1 or 1, 1 is this yes or no? Not 1, 1. So not 1, 1 means what should be the case? We should have two elements, distinct elements. It should go to the same image. Can you say such two elements? Or you can check in this condition f of x1 equal to f of x2. Does this implies x1 equal to x2? Okay, now check the image, sorry, check the domain from where the function is defined. So 1 and minus 1 will not work, right? Because it is defined in R plus. Okay, R plus means set of all positive real numbers. Okay, if you don't know the notation, R plus means set of all positive real numbers. Okay, if it is R, obviously it is not 1, 1 because both 1 and minus 1 will go to the same like image. But now our domain is restricted to R plus. Now what do you think, whether it is 1, 1 or on 2? Sorry, not leave about on 2, whether it is 1, 1. So just start with this condition. F of x1 equal to f of x2. Okay, by definition, yeah, then it is 1, 1, correct. Since domain is restricted, otherwise as you told it will not be 1, 1. Okay, now what we are considering is f of x1 equal to f of x2. So x1 square minus 8 equal to x2 square minus 8. This is our definition. By definition this is true. Okay, so x1 square equal to x2 square. So this is true since x1 x2 both are positive. Like in negative case, like x1 and minus x1 will have same square. But since x1 x2 belongs to R plus, this implies x1 and x2 should be equal. So we got it is 1, 1. Now the next question is this onto? Is this onto? Here the question is like codomain is R. Onto means like every element in R should have a pre-image. That means there should exist some x such that x square minus 8 equal to y for any y in R. So think about, does there exist some element such that it cannot be written as in the form of x square minus 8? Any idea? Think about like see, you know, like where x square is going to be positive only, and we are doing some minus 8 also. So what will be the possible range? Just think like that. So I will give the hint. X square is greater than or equal to 0 always, whatever the x. So x square minus 8 is always greater than or equal to minus 8. Okay, that means x square minus 8 attains the value greater than minus 8 only, whatever the x we are choosing. Okay, so what about the real numbers which is strictly less than minus 8? Okay, will it have a pre-image? Will it belongs to that range? For example, let's start with the minus 10. Minus 10 is a number which is strictly less than minus 8. Suppose x square minus 8 equal to minus 10. In that case, x square equal to minus 2. This is not true, right? I mean square will not be minus 2 always. Okay, it will always be a positive. That is what exactly we are doing here also. So this is actually the range. Okay, the range is from maybe minus 8 included to plus infinity. That means from minus 8 to the whole real number in that right side. So in the left side, for those elements in R, it does not have a pre-image under this map. For example, for minus 10 is not in the range, correct? In that case, what we can say, it is not an onto map. Yeah, good. Not an onto map. I hope this is clear. It is a 1-1 map. Okay, it is a 1-1 map, but it is not a onto map. That's one. Okay, now let's do a last question. This is also regarding to relation. Now the relation is given as AA, BB, BC, CB on the set ABCD. Okay. Now the question is about like it's whether it is reflexive, symmetric, transitive. So we can check 1-1 cases. First one will be let us see about reflexivity. So what do you think about reflexivity? Whether it is reflexive or not? Yes or no? Is this reflexive? What is reflexive? Reflexive means, okay, let me rewrite it. And it is given in the set ABCD, relation on this set ABCD. Okay, what does reflexive means? If I am given in, if a set is given, if a relation is given, it is reflexive if A belongs to that relation for all A in the given set. For all element from ABCD, AA should be there, BB should be there, CC should be there, DD should be there. Then only it is a reflexive relation. Yeah. So clearly it is not reflexive because AA and BB are there. That is not enough. If one or two element is there, that is not enough. We need that for every element. CC, DD also should be there. So since it is not there, this is not reflexive. Not reflexive. Now, what do you think about symmetric? Symmetric means if AB is there, AB in R implies BA in R. So first we need to check, like first we need to, yeah, symmetric, correct. First we need to start with some element, then take the opposite one, BA, whether it is there. Here A is there, it's A again, it is there. BB, BB, it is there. BC, CB is also there. For CB, BC is there. So for any AB, the other one is also there. So it is symmetric. Now what about transitivity? Anyone say? For transitive also again I can say what is the AB, BC. If two elements are there, then AC should also be there. Okay? Not transitive. Why? Can you give example why it is not transitive? For that we need two elements AB and BC such that AC is not there. See, here we have AA. but there is no element starting with the A, correct? A, C or A, D, something like that, it is not there. So we don't have anything to, A, C is not there. That's okay, right? I mean, why you need AC there? See, if like suppose AB, BC is there, then AC should be there. Okay, but here we can say AB is not there. Okay, so we don't need to check. In the same way, if ADDC, in that case also we need AC. If these two exist only, we need to check the third condition, or also AN AC. Okay, if these two are, then also we should check whether AC is there or not. Okay, these three does not satisfy because these two elements are not there, right? This kind of combination are not there. So what we need is first two elements we should choose. A, B, one element, then starting from B, B, C something. Okay, then A, C is there or not. Okay, whatever here I am given, it is in the general form, not for this particular case. Okay, here we have A is there, but there is no element starting with the A. Okay, A, B not there, A, C not there, A, D not there. So we don't need to check the transitivity condition. Here also BB is there and BC is there. So BC should be there. Okay, BC is there, correct? In the same way, BC is there, CB is there. Okay, so BB should be there. Yes, BB is there. Okay, so in this way you can check among all the elements here only. Okay, so if we are checking all the possibility, we can see it is transitive. This condition is satisfied. So it is transitive also. So what we got, it is symmetric we got, transitive we got, but not reflexive, correct? Okay, transitive and symmetric but not reflexive. This is the correct answer. Okay. So I think we can stop this today. So that's all for today. So if you have any question, you can ask now. Otherwise, we can stop for today and we'll continue in the next week. Okay. Okay, if there is no further question, let me stop for now. Thank you everyone for attending. We will see next week. Good night.